I'm going to turn things over to Bob Krovitz, our former chair, who will introduce the speaker.
Thank you, Dennis. It's my pleasure to introduce Michael Bloodgood. He's an associate professor of computer science here at the College of New Jersey. His research interests include active learning, natural language processing, and machine translation. Michael has a PhD in computer science from the University of Delaware.
All right. Thank you, Bob. So can everyone hear me okay?
I'm listening to you online, and it sounds so loud and clear.
Okay, excellent. So I'm really thrilled to have a chance to talk to you guys today. The topic is going to be a subfield of machine learning that's referred to as active learning. I want to say that right up front because I know also, especially in an educational context, active learning, that phrase has a totally different meaning about how to teach human beings effectively. So we're talking not about that one, but we are talking about the machine learning subfield. And we're going to have a emphasis on the part of active learning that deals with knowing when to stop data acquisition or when to stop the active learning process. Let's see, my slide did not go down. Something happened where my computer froze.
May need to click on the slide to put the focus on it before it'll go up and down.
Okay, let me try that. Yeah, thanks, John. Okay, so here's an outline of how this talk is organized. So first, I'm going to give an introduction to active learning. I was told that the audience could be quite diverse in their experiences and background. Then we'll talk about an important part of active learning, which are query strategies. And then most of the talk will be focused on stopping methods. And then in particular, a method that we created that's stopping based on stabilizing predictions. Then I'll wrap up with conclusions, future work, acknowledgements. And then finally, at the very end, some pointers to resources if people want to learn more or access software for actually doing active learning. So first, an introduction. This is in the context of supervised machine learning. So this is of widespread interest for developing useful systems. In this context, the machine learns a model from labeled data that can be used to predict the labels for new unlabeled data. The learned model typically works better when the machine learns from larger quantities of labeled data. So here's a graph kind of showing that sometimes a visualization helps make a point clearer than the words. So we refer to this as a learning curve. The x-axis has the accuracy of the machine learned system. I'm sorry, the y-axis has the accuracy of the machine learned system. The x-axis has the amount of training data that the machine was trained on. So you can see at the left part, at the beginning, there's only a small amount of data on the x-axis, and the machine has lower performance. And as you add data, you can see performance is going up, 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 and there's a period of diminishing returns. It slows, and maybe even by the end, it even perhaps asymptotes and levels off or plateaus. So this is with random sampling. Sometimes different curves can have slightly different shapes, but this is a good prototypical shape for a learning curve. And then the question comes up, okay, so what does active learning do? Active learning is of interest because it helps to reduce data annotation burdens. And this is by giving the learner, which is the machine, control over which examples are annotated or labeled. I'm using annotated and labeled interchangeably in this talk. So the annotation of redundant or otherwise non-informative examples can hopefully be avoided or at least minimized. So the goal is this last point. We want to select all of the most informative examples for annotation first, and then we want to stop annotating and not waste human expertise or time on annotating data that we don't need. So there are three main scenarios for active learning. The first one is query synthesis. This is where you explore whether the machine can create its own data. The second one is stream-based active learning. This is where data comes into the machine one at a time, like a stream. And for each one, the machine has to decide yes or no. Give me a label or don't give me a label. And then the last one I highlighted in red and I put it in emphasis in italics is pool-based active learning. That's probably the most common scenario of the three. And it's the one that I'm going to focus on in this talk. That's the one where you have access to a large pool of unlabeled data, and you get to choose from the pool which ones you want to request labels for. It's a very common scenario because often there's abundant unlabeled data available either for free or almost for free. And the hard part is which subsets to choose to pay your data annotators to label for you. I will mention the query synthesis. Historically, that one did not receive as much attention. However, with the recent explosion in interest in generative artificial intelligence, that one is starting to become of more and more interest also to see if machines can generate data that you can learn from. I know there might be different opinions on that in the audience, but it's something that is considered. So here's the one that I'm going to focus on, which is pool-based selective sampling. Here's sort of the pseudocode for how this algorithm would work at a high level. There are some details that need to be fleshed out, but this is the main, has all the main aspects of the algorithm. So the start, before we get into the loop, the sort of initialization, is we have some large pool of unlabeled data available to us. Let's call that capital U. We have an empty pool of labeled data. At the beginning, we don't have any labeled data. It's empty set. Let's call that capital L. We have a parameter that needs to be specified. Let's call that lowercase b. That's the batch size. That's going to control how many samples we want the machine to request labels for at each iteration. And then what's going to happen is first we need to get learning started. So we're going to randomly select little b, random examples from U, request their labels. Typically that's from a human expert. And then we initialize L to be that set. And each time we add to L, we have to take out of U. So U will get U minus L. And then we go into this loop. And this loops until some stopping condition is met. We train a new model using L. Then we select B samples from U using a selection algorithm, request their labels. That set of B samples that we select, we call that the batch. Then we take the batch out of the unlabeled pool, U, and we add the labeled batch after a human provides labels for them to L. So if you think about it, L is kind of like a growing snowball. Like it starts empty and each iteration it grows, it grows, it grows. And U, well, I don't know, a metaphor, but U is constantly shrinking. So U starts really big and it's constantly being shrunk and shrunk and shrunk and chipped away at. So that's the overall thing. I highlighted until the stopping condition is met. This is the part that I'm going to focus on in this talk. How can we make the machine know when it stops, when it doesn't need more data on its own? How can it know I don't need more data? Let's stop this process. I will also mention this selection part. Although it's not the focus of this talk, it's very important how you choose to prioritize which examples to select. In fact, I would say in most active learning research, that's the part that's received the most attention. And that's called the query strategy. And I am going to talk about that a little bit. So first I wanted to show you, this is what a typical shape for an active learning curve looks like. If you remember the other one we looked at, it sloped more gradually. Learning took place slower, more slowly. This one, since you're front loading what you think is all the highly informative, non-redundant stuff, you can typically get very sharp, very fast learning. And then because you front loaded everything that wasn't redundant, you often hit that plateau or that asymptote very quickly. And then there's often a long period of asymptote where it would be wasteful to just keep paying your expert human annotators to keep providing annotations. It would just be a waste of money and time. But the hard part is we don't actually have this curve. We can have it for research purposes after the fact with a test set to see what happens, but in a real active learning scenario, you don't have this curve. So you have to have the machine know when to stop on its own, which is hard. In next slide, I put the two curves on the same axis so you can see the difference. These are the same two graphs I showed you. So the green one is random sampling. If you make no interventions, if you don't use active learning at all, you can see because we're using the same pool of data, the endpoint over here is when you've exhausted that entire unlabeled pool. So they must end at the same accuracy because at that point they're being trained on the same set of data. But the lead up to that is quite different. And you can see the active learning curve is potentially much, much more efficient. Okay. So now we finished the intro for the main points. Now we're going to go into some little deeper dive into some of the important aspects of active learning. So the next part is query strategies. So these are the main types of query strategies that have been used in active learning. I want to say, for context, there's been a lot of research into query strategies for active learning. So there are a lot of query strategies, but they're all basically flavors of these main types and sometimes combinations of these. So probably well, I won't say, but let's just say a very, very influential one is uncertainty-based sampling. This is where you program the computer to prioritize selecting examples from the unlabeled pool that its current learned model is most uncertain about. This hopefully makes common sense. There's an analogy to human learning. Like imagine you're trying to learn, let's say, arithmetic, and you're really good at addition. You've mastered addition, but you're struggling with subtraction. Then it doesn't make sense for me to give you more addition problems. You've already mastered it. It's just sort of a waste. But it would be really efficient for your learning if I gave you subtraction problems, because those are the ones you're uncertain about that you want more practice on, you want more explanation, you want to learn about. So it's similar for the machine. You want to give it the examples that it's most uncertain about, and it can potentially learn more efficiently. Another class of query strategies is distribution-based. The idea here is if you have access to this unlabeled pool that has the space that you need to eventually learn, you want to take a little bit of each type of thing that covers that space. So imagine, well, we could use the same arithmetic example. You would want to, instead of choosing 1,000 examples that are all addition, you want to choose some addition, some subtraction, some multiplication, some division. You want to kind of spread it out and be representative of the whole space. So that's distribution-based sampling. Another one is called query by committee sampling. This is where you form an ensemble of models and you see where do they disagree, and then that's where you query. Technically, I would view QBC, query by committee sampling, as a form of uncertainty sampling, but it is often treated as its own class. So I'll just put it there. And then the last one here is hybrid methods. So it's become important to take aspects of all these main types and combine them. This has become especially important more recently with deep learning and a need for larger amounts of data than more classical machine learning algorithms needed. And because, keep in mind, in active learning, at each iteration, you're asking human experts to provide labels for you. So another thing is if you have a complex machine learning algorithm, like a very complex deep learning algorithm that takes a long time to train, you can't just like tell your human well, I guess you can, but it's not really great. Like, all right, wait, my model's gonna train for a few days, then give me more labels, and then, all right, give me, more labels. All right, now just wait. The model's gonna take several days to train and then come back. You need to kind of give the human labelers a decent workload to be working on. So with more modern algorithms, batch sizes, if we go back to our algorithm pseudocode, this little b, the batch size parameter, has been getting larger and larger and larger. Historically, it used to be, especially when just considering like the theory of this, that you would set the batch size to be 1. Like you do a single example. Select the single example you're most uncertain about, get a label on it, do this thing. But in practical active learning, and especially with more intensive algorithms, the batch sizes have been creeping up to much larger sizes. It could be many thousands of examples in a single batch. So because of that, I guess it might be clear, but let me say it just in case. If you're using like a straight uncertainty-based sampling method, if you're selecting a batch of, say, 5,000 examples, it could become a problem because it might choose 5,000 things that it's most uncertain about, but they're all the same thing. Yeah, so they're repetitive or redundant to each other. So because of that, it becomes important with batch mode active learning to combine, it's very common to combine uncertainty and distribution based, and that tends to work the best. Okay, so now I want to talk about stopping. That's really where I'm really fascinated and I really like enjoy thinking about this problem. So here's a motivation for why stopping is really important. This is a graph, this is actually a real graph from real data that we did several years ago. And the y-axis shows performance of the learned system. The x-axis shows amount of training data that it learned from. And each little data point is actual measured performance as we added data. And we used active learning, and so we got efficient learning. And what I drew here is, it really depends when you stop if you're going to really realize the benefits of active learning in practice. So even though the shape of the curve is great, like we front loaded and we learned very efficiently, imagine if you stop at this vertical line. I would say that that's too early because for a relatively small amount of additional data labels, the performance of the system went up by a substantial amount. So it's like a good bang for your buck. Like you would want to do that, I think, most users. If you stop at this line here, I would say that looks really good place to stop. That looks like a good place to stop. You're at that point, if you spend more money labeling, you're basically flat. You're not getting more gains from it, so you're just sort of wasting money. So that looks like a good place. If you stopped hypothetically, let's say out here, performance-wise, it's okay. You'd get a high-performing system, but you wasted about 30,000 human annotations. This particular one was for a machine translation task. So you could imagine if you want to bring it into practical terms, you'd have to pay your bilingual expert. I think if I remember right, when we ran this, it was on an Urdu into English translation task. So you'd have to pay an expert in these two languages to give you 30,000 more sentences translated. And what did it get you? Nothing. So in terms of performance. So the stopping is really important. The problem is, it's really hard to tell. I mean, we know we're at this point, say, if it's the green one, this sharply, then clearly we want to, I would say, label more data. We're getting good bang for a buck. Probably even the blue one, although maybe it depends on the users and their cost preferences. And then the red one, I guess probably most users would say, no, you're just wasting money. We're not getting anything. Well, okay, this is a great point. Dennis, this is a great point. There's a further problem that that this picture is a little misleading. I love this illustration, but I also don't for one reason. It's misleading in that not only we don't have this question mark part, but we don't have the blue part either. So we don't have the slope. We don't have the slope. We can have it for research purposes after the fact. we can measure it on test data and see what would it have been. But in reality, we don't even have that data to measure that necessarily. Unless, if you want to, you can pay someone to give you more labeled data to do that. And we're going to look at that as a possible way to stop. Although we have, there's one problem with that is, in a way, it defeats the original purpose of active learning, which was to minimize, get the absolute minimum amount of labeled data. So it's interesting. Okay, so main types of stopping methods. Stability-based stopping. So this is where you try to stop based on stabilizing predictions of the models as they're being learned, but it's predictions. So you don't know whether the predictions are wrong or right. You just measure whether they're agreeing with each other as they're learning. Confidence-based sampling, that's a typo. Instead of sampling, I should say stopping. Confidence-based stopping, that's where you measure the confidence of each model as you're going through your learning. And at the point where it starts to decline, you would say to stop. Performance-based stopping, this would be most like what Dennis might have mentioned here. If you're willing to pay for some other labeled data and measure performance on that sort of validation data and see how does the performance level off, that's possible. But it does have that added expense of additional labels, which is counter to the original motivation. So we have to keep that in mind. Or margin exhaustion, historically is very important. If you look at these dates, it was one of the earliest ones. And it was a good method. The only problem with that one is it's limited to only machine learning algorithms that have a margin, like support vector machines. So it's limited. It can't be applied more widely. In our experiments and in other people's experiments, it seems to be stopping based on stability seems to be working the best, which is interesting. And it has some nice features. So that's the one that I'm going to spend the rest of our time kind of explaining in more detail. So it's been kind of high level. Now I'm going to try and do a little deeper dive into how this works. So first of all, it requires no labeled data at all to make the stopping decision. I should say no labeled data, I guess, other than, of course, as you're doing active learning, you're asking for labels to train your models at each iteration, but nothing beyond that. The way it works is you take your consecutively learned models during active learning and you apply them to unlabeled data. That unlabeled data is referred to as the stop set. The stop set should be an unbiased representative set of data. There are some really nice features because it's not required to be labeled. For pool-based sampling, where unlabeled data, the assumption is that it's abundant and almost free to obtain, you can make it basically as large as you want and as representative as you want. I also think it's important if you're deploying a system and you're constantly getting new unlabeled data as time goes on and you're worried about distribution shift or something has changed, you can periodically re-update your stop set and see if things change. So it has some nice advantages in terms of that. What it does is it stops when kappa agreement of consecutive models exceeds a desired threshold. It has strong empirical performance across a lot of different tasks and data sets, far more than I ever really thought when I first proposed it. I didn't realize, but it's been cited in a really diverse range of applications. I just put a handful here. I find it kind of fun to see how diverse these applications are. So it's used in machine translation, identifying PCB contaminated transformers, technology-assisted review for litigation discovery, collecting haptic surface data for robots, filtering tweets for social unrest, peptide discovery, discovery of innate immunomodulators, semantic segmentation of 3D point clouds, and that's just a small subset. It goes on. So it's been experimentally proven to work well in a lot of settings with different characteristics. And at the end, I'll give you a reference, to the original paper where we published it. But here's just a taste, so you can get an idea of how these stopping methods work. For each task or data set, I have several stopping method columns. And then the last column is important. That's if you use the entire pool of data. This would kind of be like standard passive supervised machine learning with no active learning. Like just take all the training data, just pay someone to label it. Don't worry about stopping. Just label a large amount of data, train a model, see how well it works. So you can take, for example, the first one. This was a classification task for classifying a text document, whether it's an email document or a spam document. And the stabilizing predictions column is here. It says to stop when you only labeled 2,100 examples out of the 56,000 in the entire set. And the performance is 98.33, which is almost the same as 98.47. So what this shows is it's not a small thing. Like you can save a lot of annotations and get essentially the same performance. But it does depend on data set. You can see different variations in the table. But it's overall a pretty stable method. It works pretty well. Well, I guess that's enough for that. Like that's just showing kind of how you can save. So experimentally it works. But then what's interesting? Oh yeah. Oh, I'm sorry. What was it? Oh, yes, exactly, right. Every one of these, they use the same experimental parameters. So all the same data, all the same parameters, like for batch size, the same query strategy for prioritizing or sampling, the same base machine learning algorithms, all these things were kept the same. So the only difference is the stopping method. Yeah, Bob.
The ZW8
Yeah,
2008.
yeah.
I noticed that it tends to do better. The cases are doing better with less data. If you have all the data, then
Yeah,
I'm
that's
wondering what's going on there.
Yeah, that's a great question, Bob. That does happen sometimes, not only for ZWH, but probably for all of them. There are some cases where that could happen. That is a phenomenon in active learning it has a really fun name. It's called less is more. It's called less is more. And so sometimes those learning curves, like if we go back well, this one was a real one. Even this one, not so much. This one's kind of flat. But you see how here at this point it dips down a little bit, ever so small. This can happen where sometimes with a smaller set of data, you actually get higher performance than with more data. And some examples are a bigger amount of dip than that. Some of them actually go up, have like a little peak, and then go down a little bit.
Like a local minima type of.
Yeah, I guess the explanation is noise. So you front loaded like all the priorities stuff, you've learned the core concept, and sometimes that redundant stuff just has like some noise in it that just brings it down a little bit. It could also be some overfitting. If you just keep training, it starts to overfit.
Yeah.
So these things, yeah. That's a great question. Thank you. Yeah.
Let me just see if I
Okay, go ahead,
my
Dennis.
understanding is clear.
Yes.
What you're doing is you're saying, I'm going to have this stop set that I'm never going to show to real humans to classify, right?
Yep.
But what I'm going to do is after each batch or after each 10 batches or, every so often,
Mm-hmm.
I'm going to use my learning system
Mm-hmm.
to basically go through all of those things.
Mm-hmm.
And I'm going to compare the results. How many of them I get the same answer? How many of them I get a different answer? Because it's learned, right?
Exactly. Yeah.
And if the the um, the same answer keeps coming up, that means I'm not really making any progress, although these things could be wrong,
Yes,
but at least they're consistent from one
exactly.
round to the next.
Yes, you understand it perfectly then.
Oh,
Yeah.
oh, oh. That saves me all kinds of money actually having to hire people
Yep,
because I can run
can
the
stop
model as many times as I
as many
want
times as you
to
want
at
for free.
nighttime or on
Yeah,
on the cloud or what have you. Oh, yeah. Okay,
yeah,
I got it.
yeah.
Okay, thank you.
It's perfect. Yeah. Sometimes it might help. I didn't really give the history, but this kappa statistic, I think this was created in the 1960s by someone named Cohen, and it was originally, it had nothing to do with computer science. It was for psychological educational assessments. I think for many decades, and even still today, probably, the kappa statistic is really used to measure agreement between human beings. So you could think of it as like, I give person A 100 questions, maybe a test or something, and I give person B the same test, 100 questions.
Yeah,
And then I measure how much does person A agree with person B,
yeah,
but I don't grade them. Like I don't say like say person A and person B, they answered 99 of the questions with the identical same answer. There was just one question where they disagreed. I can say that they have very high agreement. They
yeah.
will have a very high kappa, but we know nothing about whether they're very high, accuracy or correctness of their answers. Yeah, this thing.
So in fact, this would never happen if you were giving an economics test because every economist disagrees with
Oh, I
every
see.
other economist, right?
Yeah, yeah.
But
Well, they would have a
lawyers,
low kappa. They would disagree. Yeah.
but lawyers, I mean, they converge, right? They think, okay, so they'll probably be pretty good.
Okay. Yeah, Bob.
So this, the other stuff you were talking about on what I would call ensemble learning.
Mhm.
You've got a number of weak classifiers, and together that you get strength by combining them.
Mhm.
Is this looking at the kappas? Can you apply that to the ensemble thing and say how much agreement do I have between the different ensemble learners,
Mhm.
and which of these ensemble weak learners do I have the most confidence in that they're the smartest? And I
Oh,
should maybe give a little bit of strength to not just to the ensemble, but to the member of the ensemble.
yes. That's another excellent question. That one, I would say yes, but it's a different thing. So, like, yes, that's a good idea, and people do that when they do the query by committee for the sampling for choosing. They will measure this agreement or disagreement, depending on your perspective. These are just like flip sides of the same thing between these models in the ensemble to figure out what data to prioritize to ask for labels from. So yes, but I just want to make sure everyone knows, but that's for the sampling part. Here we're using it for each model as learning is progressing, model like at time t to model at time t plus 1. So even without ensemble, like a single model, but then to the model learned at the very next iteration of the loop and see how much they agree. So absolutely yes, there's that similarity, but they're for different purpose. Yeah, through a committee. Yeah. So
We have one question online here.
Okay.
Neil asks, does this rely on some uniform distribution of the unlabeled data? What happens if the unlabeled data is longitudinally skewed such that, for instance, the early items are not representative of the entire corpus of the unlabeled data?
Wait, I couldn't hear the last part. What was the last part?
What happens if the unlabeled data is longitudinally skewed so that early items are not representative of the entire corpus?
Okay. Wait, can I ask a follow-up? What do they mean by early items?
That's not clear. I think
Okay.
what they're talking about are the ones that basically are in the early batches.
Okay. Yeah.
On your data is not stationary.
Yeah, this is what I'm wondering. Are we talking like, that's why I was trying to clarify the early. Like, are we talking about early during the training process
Yeah.
where we're adding to that growing labeled set? Or does the person who's asking this or the people who are asking this have a notion of for the unlabeled stop set that like the data the system would be deployed on is changing over time. Because I
Aha.
think my answer would be a little different depending on which one is being asked about.
Okay.
By how? By
To both? Yeah.
constant. So naturally, because we were sampling in time, something that is time dependent, you are going to be introducing different regime shifts on the underlying distribution as you sample. So I think that fits both aspects of it.
Yeah, that's a good question. That's almost similar to the thing I mentioned before about using it for detecting distribution shift. So the answer is a little bit complicated, but not that much. So there is an assumption in a way for the person, the remote person that you mentioned,
Yeah.
that isn't an assumption that it's sort of stationary or this kind of thing. There would be an assumption if you're using a static unlabeled pool and a static stop set,
Mhm.
there is an assumption that that stop set is representative of the application data time or the application time unseen examples on which your learned model will be used for a useful purpose.
Okay.
So you want to make that representative of that space. Now, if there's a concern, and there certainly could be for many applications, that application time space of examples will be changing, their characteristics will be changing over time, then, but this would affect, all static supervised machine. I mean, this is not like particular to this in any way. And in fact, I like the question because I think this, if anything, gives a little bit of an advantage for that, is that you would have the ability to periodically get a new stop set because it's so cheap, because it doesn't have to be labeled. Get one every so often. If you're afraid that your situation might change on a yearly basis, every year get a check in and see if it still agrees. If you're afraid it might change on a monthly basis, every month, take a new snapshot, like a stop set, and check in on the agreement. If you think it's faster, you can do it at any granularity you need. If you want to do it every night, overnight, or something. So this, if anything, I think this will give an advantage on that over, the standard is just train your model and use it, right? Yeah. Yeah, so I like those questions a lot. Okay. Yeah, that's cool. So let's go back here. So we're stopping when kappa agreement, this thing, and I want to start to dive into a little bit of the like theory of why we can expect this to work. So, and this also gets a little bit to your questions too. How it does assume that that stop set is representative of the space. It does assume that. But it has the nice advantage that you could change the stop set if you think your application time, there's some drift or shift of the distribution. So here, I want to keep in mind when we're measuring that kappa statistic between the models, we're getting a sample estimate of it. So that's this table over here. In theory, we don't know it, but we can imagine that there's a true population phenomena and there's a true kappa. Our estimate is based on these counts over here. So we have some number n, and we can take model m sub t at iteration t and compare it with the model just previous at iteration t minus 1. And we can say, let's say for simplicity, it's binary classification. We can say how many times did both models say positive, predict positive? And we count them and we say that's A times. We count how many times did model T say negative and the model just before that disagree and say positive. And we count them and that's B times, and so on and so forth. And we get these counts, and from these we get a sample estimate of kappa, and we have to keep in mind it may have some variance from the true kappa. And so we use a method to compute the variance. And this is a little bit complex. And probably for time, I shouldn't go into like every single detail of this. But the really important part that's pretty easy to understand pretty quickly is this n in the denominator is the size, that's the size of the stop set. That's all of the number of examples in the stop set. So as that gets larger, because it's in the denominator, it brings down the variance of our estimate, which accords with your intuition. Like you're going to get a better estimate if you use more data to get the estimate. And the other part that's important is P sub E is our estimate of the amount of time that the two models would agree just due to chance. And if that gets really high, like close to 1, we could have a problem because this number will get close to 0, 1 minus 1, and then squaring it will get even closer to 0. And because it's in the denominator, that will make the variance get very high. So if we have an application setting where P sub E can be expected to be close to 1, usually this happens for very imbalanced data applications, like needle and haystack kind of applications.
You're looking for decay products in a physics experiment, and it's neutrinos going through
Yeah,
some
something
huge
very
vat,
rare,
and
a
you get
very
and you
rare
get
event.
1 every 6 months.
1 every billion, yeah. That one, this would be a concern to use this method because it
Okay.
could make it explode. So the upshot or the implications is that the variance is inversely proportional to the size of the stop set. So that would say, all else equal, you want a bigger stop set. But this is interesting. We can add a variance check to the algorithm to improve the algorithm. So because this computation you can do just on the stop set as you're doing active learning. It doesn't involve any other data being needed. So you can get that variance as you're going. And if it exceeds some desired threshold where you think, oh, this is getting too risky, I don't want that high of a variance of my estimate, then what you can do is say, okay, let's increase the size of the stop set because that would likely reduce the variance because that n is in the denominator here. And then there's also another implication is this warning that when PE is relatively close to 1, the variance can be expected to get quite large, which is very risky. And therefore, you might want to reconsider whether you want to use this method or at least be aware of that danger. Okay, cool. So here's a theorem. We really dove into the theory of this. My collaborator, John Grothendieck, and I, back in 2013, we published this theorem. Before this, we had used this method that we just discussed, stopping on stabilizing predictions. Other people had used it, and empirically, it was working well. It's like, oh, that works well. It's like simple, it works well, okay. But what about like why? Like, let's try and understand why is this experimentally working well? What's the key? So what we did was we started to analyze the math of it. So let m sub t be the model learned at iteration t of active learning. M sub t minus 1 be the model learned at the just prior iteration. So consecutive iterations. Let k sub t be the estimate of kappa agreement between the classifications of this model, the most recent one, let's say, if we're at time t or iteration t, and the just previous model on the examples in the stop set. Let f tilde sub t be the f measure between the classifications of m sub t and truth, and real truth, like if you asked a human expert to give you the true label. So truth on the stop set. Let f sub tilde sub f t minus 1 be the f measure between the classifications of the just previous model and truth on the stop set. Now, you might ask, wait a second, how are you going to get this truth on the stop set? I thought Michael, you just told us we don't need labels for that, right? True. Now, this is almost philosophical. This is really fun to think about. Although we don't know the truth, the true labels, still some truth must exist. We don't know it, but it still exists, right? So we can think about it. So this gets fun. So we may not know that truth, but we can conceptualize it, and we can certainly call it f tilde sub t, and it exists. We may not be able to compute that number and say like it's 96.32, but we know it exists. So then what we do is we let delta f sub t be subtracting those. So f tilde sub t minus f tilde t sub t minus 1. And we suppose that some threshold, let's call it capital T, is greater than 0. Then if the kappa sub t is greater than that threshold, that implies that that difference in f measures between those two models, m sub t and m sub t minus 1, must be less than or equal to 4 times 1 minus the threshold divided by the threshold. And that's mathematically provable beyond a doubt. You know, that's just always true. And it's a worst case bound. It will often be much less than that. It's less than or equal to. But it must be less than or equal to that. Now, for intuition, if you're thinking, okay, that's a lot of math, whatever, this thing, it is. But it also is very intuitive if you step back and think about it. Remember we said like this kappa is measuring, imagine the two students, I gave the example, or two people. One takes a test of 100 questions. Person B answers the same 100 questions. And I had said they both answer 99 of the questions, exactly same answer. And there's only one question that they disagree on. And we don't know their scores. They may have really low scores. They may be answering almost everything wrong. They may have really high scores. Maybe they're answering almost everything right. But you do know, even without doing this rigorous math, just intuitively, you know, if you did get the truth and grade like both people's exam, their grades must be very close. Their grades can at most differ by, if each point is worth 1%, their grades can at most differ by, I guess, 1%, because 1 out of 100 that they answer differently. So you do have this intuition that, oh yeah, of course, if they agree by a high, like above that threshold, capital T that we call it in the theorem, then it makes sense. Yeah, you could bound, they can only differ in performance by so much. And it's a function of that threshold.
So
Yeah,
not only they're either brilliant and agree with each other, right? Or they're both dum-dums, but through some
Oh, I see.
magic,
stroke of coincidence.
yeah, they all got the same wrong answers.
Yeah. Or maybe they were true false questions or something.
Yeah.
Some kind of, yeah. Or like systematically got it wrong. Yeah, exactly.
Yeah. So, some psychic connection.
Yes. Bob.
Just puzzled why the 4 it is.
Okay. Okay. The 4. Actually, that will be answered. Let's take a look. Let's take a look at the proof. So how did we go about proving such a thing anyway? So the challenge is, yeah, because I can't just, the answer is, yeah, we have to go through this to see the 4. We'll get to the 4. So the challenge is F measure seems to require having knowledge of the ground truth, which we don't have because it's a stop set of unlabeled data. The insight, how we were able to prove this theorem was we said, look, we can still bound the difference without knowing the ground truth by assuming a worst case scenario. So worst case, I put it in those single quotes in the sense that every time they disagree, we assume that it's going to be, the ground truth will be in such a way that it pulls them to have maximal difference in performance. This is the picture. Sometimes the picture helps understand it. This one up at the top is the same one we had before. That's our contingency table, our standard contingency table. N is the size of the stop set, and we have A times, they both say positive, and so on and so forth. What we do is we split this. When we go this way to this table, we're taking every example from this top table that is truly positive. So A sub 1, this number here, that's the number of times that model T predicted positive, model T minus 1 predicted positive, and it's truly positive. Now you're saying, wait, we don't know the truth. That's right, we don't know it, but it must exist. Like the number still exists. We don't know the value of A1. We know the value of A. We can count that on the stop site. We don't know the value of A1, but we know it must exist. And the same, analogously for this one, this is all the ones that are truly negative. So for example, to understand the format, A sub minus 1 is the number of times model T predicted positive, the model just prior predicted positive, but it was truly negative. Yeah. Again, we don't know the value. We don't know because we don't have the labels, but we know it must exist. And so you can, from this powerful set of equations that must be true. So for example, I hope everyone can see, like a sub 1 plus a sub minus 1 must equal a sub 1. Boom. Another one, b sub 1 plus b sub minus 1 must equal b. And we keep going. N sub 1 plus n sub minus 1 must equal n. So we have this powerful system of equations now to work with. And that gives us some power to really delve into the insights and see where Bob gets the magic 4 from. It's coming. So from that, it follows, and this is a limited talk, so I'm not going to give all the math. But if you want, you can look at the BG, the Bloodgood and Grothendieck 2013 paper, is all the math, like down to the bones, if you want to really do every line. But delta ft comes to this in terms of those variables on the previous slide. It can be proven that it comes to this. Then there's a fair bit of intervening algebra. Some of you, I see, have read that paper. Yeah, there's quite a bit of intervening algebra. But it eventually simplifies that the absolute value, that difference, that delta, must be less than or equal to, and it comes to 2 times 2a, 1 minus t, this thing. And this is where we get the 4, Bob, the 2 times 2, yeah. So that's a little bit of an abbreviated explanation, but in the paper you could also read this ... There are many lines of math, and you can see. But it comes to this times, but it's not done. It comes to less than or equal to this, 4, 1 minus t over t, times this fraction, where we substitute the values from the previous slide into f d sub a and d sub b. So everything is in terms of these variables. So the key insight, I would say, for the proof is this breakdown. Understanding that even though you don't know the values, they still exist. You can give them names, and then you can form equalities and inequalities, and then manipulate them mathematically and come to this bound. Now,
I think we lost the camera.
just look at the first one, like a sub 1. If we go back to the meaning, a sub 1 means model T said, I think it's positive. The model just before that said, I think it's positive. And over your entire stop set, you're saying every time both of them say it's positive, it's never right? Like it's always wrong in order for that to be 0, right? Yeah, it would be really bad machine learning, right? Yeah, I mean, yeah. Yeah, it would be really pathological. But to keep the bound like mathematically true in all cases, technically, yeah, in theory, it could, happen. So, but it's important to note, because moving toward the practice, in many practically important classes of cases to consider, this will, of course, be strictly less than 1. And actually, often it's substantially less than 1. So that bound that we gave, it's often practically loose, although you do need it for that pathological case, this thing. And experimentally, we ran this on a lot of different data sets and tasks and measured it. It's often much lower than the bound. So here's something to try to, how can we tighten the bound? So this gets at the point of, we can quickly cut the bound in half. And Bob, we can change the 4 to a 2 pretty quickly if we're willing to make this assumption. This is that if we assume that M positive conjunction is a model that only classifies an example as positive if both M sub t and M sub t minus 1 classified as positive. Suppose that that model, M positive conjunction, has perfect precision on the stop set. Or in other words, that every single example from the stop set that both MT and MT minus 1 classify as positive is truly positive. Then we can quickly cut that bound in half to 2 1 minus T over T. Now, you might say, okay, but that's unrealistic. Is it always, perfect precision? True. So here's a more generalized form. Let's say it has precision P, because the first one is also pathological, is unrealistic, but 100% might be unrealistic. But say it had like 90% precision. So let's say this little p was 0.90, then you would get 4 divided by 1.9. So we're cutting it also, not quite in half, but this thing. So now we're up to getting close to wrapping or this thing. Conclusions, future work, and resources and stuff. And then we'll also have more time for questions at the end. So main points. Active learning has the potential to reduce data labeling costs by large amounts without sacrificing model performance. However, in order to realize that potential, effective query strategies are needed to prioritize which data to label. That was not the focus of this talk, but that is a very important part of active learning and probably the part that has received the most attention in research, actually. But I would say, and effective stopping methods are needed to know when to stop. Stopping based on stabilizing predictions has been empirically successful in a lot of experiments, and it also has reinforcing intuitive explanations based on math of why it should work well. Just to summarize what those were, we can have low variance estimate of prediction stabilization as measured by kappa. We have tight connections between the amount of stabilization and the amount of performance differences. So there's a tight linkage of those. That was what the theorems proved. And we have the ability to check for prediction stabilization on large representative sets of data that are not required to be labeled. And then we had that really good question, what about a really tough case where distributions are changing over time? And I would say there, this thing is by itself, like if you leave it static with a single stop set, yeah, it's susceptible to those problems. It does assume that that stop set is representative, but more so than a lot of other things, this at least opens the door that you could swap in a new stop set if you think your distribution is changing and detect distribution shift that way. Future work is important to consider. So the need for user adjustable stopping was identified at least as early as 2009 in this paper. I'll give you the reference at the end. And recently, but it didn't solve it. It just said like there's a need for user adjustable stopping. And what I mean by a need for user adjustable stopping is if we go back to the curve, one of these curves, where was the real one? Here it is. Okay. So it can be debated. I think most users probably wouldn't want to stop here because they're still getting some decent performance gain for paying for a modest amount of additional data. But that can be debated. If someone really has a high labeling cost, like you have an application where your expert is so highly trained and their time is so expensive that it's so expensive to label and get new data, maybe you don't even want to spend that extra money. Maybe you just want to stop it here or maybe somewhere in between these lines. So I do think there's not like a single necessarily optimal stopping point. It will depend on application setting and a particular user's cost values. It also depends on what's the value or the cost if your machine learning model makes a mistake. So if your application is like, yeah, okay, as long as the model is 95% accurate, that's good, my customers are happy. It doesn't really matter that much when it's wrong, or even maybe 80% is good for you then. It's like, yeah, it's wrong, okay. But if your application is like, I don't know, like life sensitive, or there's huge amounts of money on the line or something, anytime the system makes an error, then you might be willing to spend a very large amount of money on data labels because every little bit of performance you can squeeze out of it is worth it because the stakes at application time are so high. So These things are important to trade off. And recently, there was a breakthrough on how to evaluate this. This Puller-Strecker et al., I'll give you the reference at the end. They came up with a really nice way to evaluate stopping methods in terms of how well they work for different cost values. And I'll show you the picture that illustrates that nicely. The y-axis is your labeling cost. So it's how much you have to pay for each label. The x-axis is your error cost. So that's how much of a cost do you face every time your system gets it wrong. So you can shade, the way their method works is you shade the region where different stopping methods have the best performance. So it's not like there's a single optimal stopping point anymore. You can take cost into account. So the shadings here, this is stopping method 1, is this slice over here. This big one in the middle is stopping method 2, and this one down here is stopping method 3. And so this is hypothetical. This is fake just to show the point. Is this slice here would mean when you have relatively low error cost. So it doesn't matter that much if your learned model makes an error. Like, sure, it's better if it gets it right, but it's not like life sensitive. Maybe there's not that much money on the line. It's that kind of thing. But you have relatively high label cost. Then you would prefer this stopping method. If you're somewhere in the middle, you would prefer this other one. And if you're in the other scenario down here where you have very high error cost, so you want your final learned model to be as high performing as it can possibly be, and relatively low label cost, so you can get more data. I can buy more data. It's not that expensive. Then this stopping method would actually be better. So there's a little bit of interesting new evaluation framework. And that's also an area of future work, our lab, and some of you in the room are working with me on that. So that's an interesting project we're currently working on. So before I wrap up, I want to do thanks all my former collaborators. A lot of fun to work with, and a lot of the papers and these ideas I told you about were through collaborations with these folks. My current research students here at TCNJ, they're really doing some fine work on these areas, and hopefully we'll have some new contributions coming soon. Acknowledgement for the funding and stuff like that. So some of this research was supported by the SOSA and MUSE programs of the College of New Jersey. And we very heavily use high performance computing in our experiments and our research. And we use the ELSA HPC cluster at TCNJ, which is funded by the National Science Foundation. So we thank them for that. And before we leave, if some of you are interested in learning more about this, or you want to use software to start running your own experiments, here are some nice resources. There's been several active learning software packages that have come out recently. We're using this one called Small Text. The lead creator is Christopher Schroeder, and it's from Leipzig in Germany. And we found it to be really good, very clear. It's easy to read the code and understand it. And maybe most important, the developer of the software is very responsive, and it's very actively maintained. And so if you're interested in coding up active learning stuff, that might be a nice start if you don't want to have to code it all from scratch yourself. I do have to add, though, it is primarily geared toward NLP, or natural language processing. So it has a lot of bias toward working well on text data, because that's what most of our experiments are on, NLP tasks. And there's a paper reference. Also, here are some really good, more general purpose references if active learning is somewhat new for you. Starting at the bottom, this is an older but kind of classic literature survey that has a lot of great basics and foundations for active learning. And then more recently, going to this top one, this is a general survey of deep active learning, not just for NLP, but for more broadly, but specifically for deep active learning, like with deep neural networks. And it's very comprehensive and very thorough. I find it very informative. And then because we do a lot in NLP, and I know a lot of you actually in the audience also do NLP. So here's an active learning survey specifically for NLP, also pretty recent. And it's also, they did a good job within the space limits. I think it was published in EMNLP, which has the page limits, and they did a good job of concisely getting the most important points into it. Here are references. I'll share the slides. People can look at references if they want to go deeper into any of these subtopics that we talked about. And then, if there are more questions, I'm happy. I don't know. It's up to Dennis and Bob, and yeah. Okay.
We will make sure that we put the slides on the downloads page of the chapter website.
Okay.
And
Sounds
there will be a link to the video also.
Okay, sounds great. Yeah.
All right. So we'll get that in the next few days.
Okay. Yeah. So do we have time for any questions?
We do
Okay.
have time for questions. So, Bob?
Well, I'll let somebody else go.
Here is one. Okay.
Yeah, so just 2 points of clarification. Your F measure, is that your F score or F statistic that you're constructing?
Yeah. So F measure, what you know about, like sometimes they call it F1 and sometimes they call it
F1, yeah,
F1
F1
score.
yeah.
They use
Okay.
measure and score interchangeably. So it's the harmonic mean of precision and recall. Okay.
Yeah.
Yeah.
And then for kappa, is that a distribution-free statistic? Or is there any underlying governing distribution for kappa or its variance?
I think it's distribution free. Yeah, I think it's distribution free. Like it doesn't assume normality or something like that. I don't think it does.
Okay.
Yeah. Well, I might be able to explain a little more about kappa. I'm not 100% sure about that. I would need to look at that. But I think how I think of kappa is when I think first, like if I didn't have someone else's thing, like I just think, how would I measure agreement between two things? The most easiest thing that I would think of, the first, like simplest, most obvious thing, is let me just take the percent of times they agree. So I would just say percentage agreement.
Right.
The problem with that kappa sort of remedies, is when you do percentage agreement for these imbalanced data sets, you can trivially get a very high percent agreement just due to chance. And so like everyone's gonna have 99% agreement, this thing. What kappa does is it factors out and it takes into account what's the amount of agreement that can be expected due to chance. And it takes that out and then it, that's my understanding of the point of it. Yeah. But by the way, I should also mention, I don't really think, I mean, the kappa statistic is cool and there's that thing, but I think the stabilizing prediction, stopping on that, and we've done some research on this, I think the key thing there is really like the power of this unlabeled stop set and this idea of measuring agreement between the consecutive models. But the exact way you measure the agreement, I think it's good to keep an open mind. We've done some research where another statistic called Gwett's AC1 statistic actually did better than kappa. Several years ago, we had another one, well, I should say did better than kappa for some scenarios, particularly some imbalanced ones. We also did, there's another metric called Krippendorf's alpha, which also is an agreement type of metric. It also is competitive with kappa. So I think keeping some idea of, like, feel free, like if you're planning to do this in a project you're on or for your company or university or whatever you're doing, any of you, I would say feel free, like if you think there's another measurement of agreement that you think might be more natural for your application than kappa. And some of those citations I gave of the wide array of applications where the method's been used, some of them use kappa like we did in the original paper, but some of them did not. Like some of the computational chemistry ones, they just use some complex formula measuring, I didn't even remember all the details, but a complex formula of how well things matched up. So yeah. Yeah, good question.
Bob.
Okay, Bob.
Thank you, Michael. Very good talk.
Thank you.
There's a couple of things I'm thinking about.
Okay.
One is in the first slide that you showed, your baseline with no learning was 95%.
Okay.
So you might not, with the user criteria, the user might say, that's good enough. I don't need to do so where you're starting from is also a factor.
Oh, I see. Right.
Um,
Right.
there's a couple of things that I was looking at. One is the notion of the kappa over time and the kappa among weak learners that you have. And I'm wondering about the hybrid of looking at the combination of the two of them. You've got agreement among weak classifiers, and you've got agreement over time over the next things. The combination of the two strikes me as being especially powerful.
Definitely interesting to think about. Yeah.
The other thing I was thinking about is multimodality. So one of the big things that we've got now with deep learning is they combine images, they combine text, and you get things like heat maps on the images based on the things that you can. So I'm wondering about active learning between the different modalities of saying I need to do on this stuff because I'm uncertain. I've got something, or the images are contradicting what I'm seeing from the text. So I need more sampling of things from the text. Something like that between the modalities. Is there work going on like that?
Yeah, these are complex questions, Bob, complex thoughts. I in our lab, we haven't done like the multimodality research. Like we're solving, if I understand it right, you're asking about things where we have like a computer vision model and we also have an NLP model and they're being used synergistically
I've
somehow.
known that there's work in, when I first heard about active
Mhm.
learning, I heard about it from computer vision.
Yeah, it's definitely the history of active learning, probably the well, first, I guess there was learning theory community. Like they just like theorized about it. But then definitely I would say the two application areas that really drove its progress early on were computer vision and NLP, which also kind of drove a lot of just machine learning's progress. Like these were the two things, and more recently other fields. But yeah, I haven't worked on mixing like the different modalities. So I'm probably not the best one to answer that. Yeah, I'm not, I don't know that much about that, but it seems like it could be done. It would add a lot of complexity of how to sync those up and put them on a sort of an exchange rate to kind of unify them. So their measurements, this thing.
We have a
Yeah.
question from online. I see Josephine has her hand up, and then I'll call on Terry next. But Josephine, you should be able to unmute yourself, and we would be able to hear you.
Yeah,
ahead.
thank you so much. Really interesting talk, Michael. Michael, could you possibly go to your slide that has the grid where you compare various data sets?
This one.
Yeah, that one.
Okay.
The task data set. I noticed that several of them look like they're protein folding. And I'm more familiar with the AlphaFold protein structure database. I was just wondering if you could say a little bit about I don't know, just if you
Yeah.
could just add a little bit of information.
Yeah, thank you. Yeah, I should definitely talk. Yeah, I should explain that a little more. Yeah, I didn't explain this in detail, just to give the gist of it. But so each of these are like a task data set. And this one, the NER protein with the tenfold average, it's actually not protein folding, but I can see why you would ask that, of course, from what's written there. So I should clarify that. What that test is, it's actually it's a natural language processing task. We had a bunch of text from biomedical literature and like scientific literature. And the idea was, can we make the computer read those articles and automatically, NER stands for named entity recognition in this context. It would automatically identify everywhere in these scientific articles that the name of a protein occurs. And then the idea was later software would then compare pairs of named protein occurrences in the same text vicinity and potentially automatically populate databases with certain important protein to protein relationships that are being published in the new scientific literature, like certain important protein-protein interactions that occur. And the reason it says fold, yeah, because yeah, it is little, it does need explanation because the way it's written. That tenfold average is just that we experimentally, for the robustness of the experimental results, we did cross-fold validation on it and we ran it with 10 folds. And then the numbers in the grid here are the averages over each of those 10 folds of experiments for each one. So yeah, that definitely needed more explanation. Yeah. I think,
Okay.
but now I think, it makes sense now, right? Yeah.
Yeah, it makes a lot more sense now. And thank you. And I just want to thank you again. It's very interesting.
Thank you. Yeah, thank you.
All right, let's also go on the line here to Terry. Terry, you can unmute yourself and ask your question.
Well, Michael, first, just thank you for the excellent talk. I was very impressed with the results, especially how multidisciplinary the results are. That's a good sign. It shows that you're getting at a pattern that goes much deeper than just a local set of problems. You're getting something that's very cross-disciplinary. So I was impressed by that, the breadth of those results with that. My question is pretty broad, but my security background showing active learning in the presence of malicious intent. Is that an area that's been studied? Have people looked at that aspect of active learning? When we tend to trust our data, but it is certainly possible these days, even more so these days, that you can have mixes of nefarious intent as well as malicious intent as well as good data.
Wait, Bob, did you hear all that question? Or can you guys in the audience, or Dennis, you heard that? Okay. On Zoom?
Telling us like a security question.
Yeah, I heard it. I heard it. Security background. I had trouble hearing some
Malicious,
words were falling
Like
out. but, yeah.
imagine data poisoning in the loop of active learning.
Imagine data points being what?
poisoning in the.
Oh, so
Poison.
people. Oh, okay, so people are maliciously injecting
Can I-
like false labels.
Can I try one more time? Can you
Oh,
hear me better
yeah.
now?
It's much louder now.
We
Wow.
can hear you now.
Okay.
Okay, go ahead.
Maybe too
Well,
loud. Dennis.
I'm doing the microphone in the mouth thing here. First of all, great talk. I love the breadth of your results, how many different disciplines that your data applies to. That's a sign that you're getting something deep. You're not just getting a shallow result. You're getting something that crosses almost every discipline, and that's always a really great sign. So my question was, and I think you quoted it pretty well,
Okay.
active learning in the presence of malicious intent or intentional poisoning of the data. We tend to be a very trusting lot, but of course these days it's getting more and more, it's getting more risky, not less, about there can be malicious intent and even forms of data you might not expect. So I don't know if there's research going on in that area. That could probably be a whole topic by itself, but just comments on that.
Wow. Okay. Yeah, that's a great question. That's a really good question. I can answer it in a few ways. So one part of the answer is I'm not doing security research myself. So in part of the answer is that I don't have the knowledge to be able to fully answer it. So I'm not sure how much there is or is not being done specifically for those security applications. So that's unfortunate, but I just don't know that. But the part that I can answer is research almost more from like a more general perspective. There is research that deals with like active learning in conjunction with noise in the data. And some of that research might not be as specific as your question. Like some of that research may just be noise that innocently occurred in the data due to genuine mistakes. But it may still have a bearing on the things that you're interested in or the things that your question motivates, because I would guess that some of those techniques and findings, even if it's for noise not necessarily maliciously injected, but that occurs for perhaps innocent reasons, some of those techniques and findings might also be helpful for people who are trying to adapt active learning to help with security applications where maybe it's known that there are malicious injections. Yeah.
Okay, interesting. I would make one comment that may be a research area that people who are interested in some of these areas could certainly be something to look at. One of the problems with malicious intent is, to a degree, noise will help, noise prevention will help, but malicious intent subverts the idea of noise. It intentionally tries to look like a good signal when in fact you're getting both signals. So one of the things that comes up in security software is that you have to look for the really sneaky one. But this could be something where active learning could be a strong participant and helper in this. So it just sounds like something that might be an interesting research topic. So,
Yeah, I agree. I think it sort of seems to have some natural synergies or some natural points where they can help. I agree. It might even be something. Yeah, some of us. I see some folks in the room doing research now. Yeah, we have some research on the more innocent noise that we're working on. We might. Your question might help us look into some other areas as well to improve that research. So yeah, thank you.
Okay, I think we're gonna call it quits.
Yeah.
Except that for the folks that are here, we can have some informal discussion, and there's goodies over here too. So dig in and chat, and thank you for everybody who joined online. It's going to be all virtual next month, and Terry's going to be our speaker. So looking forward to hearing what you have to say about quantum. All right,
Very good. Yep.
we'll see you all later. Bye-bye.